All right. Well, I think we have essentially a complete group of people here, or just about, and maybe a few will join us. So I wanted to take about half the period to talk a little bit about the exam. I think everyone did just fine, and so I'm not particularly concerned. There were a few things that caught my attention on it that I'd urge. I think it just will make people more effective. Honestly, for me, exams are a great way to get a feeling for what people have learned, where deficiencies are, and basically how to communicate better. So for most people, and I think what I'll do is share my screen and probably just flip through all the problems and talk about things that occurred to me on Sunday night as I was sort of going over them. I've already, I think for all of you, marked on your exams basically corrections. So you should effectively from your own exam have an answer key. So I guess one of the things, and of course, for anyone who found the exam challenging in some ways, or didn't do as well as they want, or just was frustrated, the one thing I would urge as a general instruction is make sure to read the instructions. So I know a couple of people missed that this was aliphatic carbonyl compounds. But and the other thing I guess I would urge people to be able to do is really read analog scales. And that was one thing I noticed as people went through and came up with esters and anhydrides and tertiary amides and aldehydes and ketones. I think the numbers for a simple, and we were trying, James and I, well, James really put this problem together. James was trying to come up with very characteristic examples. And I guess the other thing I'll mention, these were all super small molecules. Many of them were 4 carbons or 5 carbons. I think the biggest was 8. So the functional groups are really strong. I think one of the things I saw, at least as one thing I'd urge, is realize the fingerprint region can be tricky. And so, I think in the ester here, for example, it is easy to pick out the CO single bond stretch in addition to the CO double bond stretch. But I think at least a couple of people got tripped up and maybe put more emphasis on what they were seeing over in the fingerprint region than the characteristic carbonyl stretching frequencies. I didn't want this problem to be tricky for anybody, and certainly we didn't incorporate any sort of traps into it. I think the other thing that's useful is to get used to the idea of figuring out what can be, where you can pay attention and where you can ignore stuff. And so, for example, something like this just does not scream out as alcohol or anything else. And I guess I tried to hint that these were monofunctional. Ditto over in the tertiary amide, with our characteristic 1660 or thereabouts, recognizing that this is not anything significant was sort of useful. Does anyone have questions or comments on problem 1?
I had trouble with spectrum B.
With spectrum,
I'm not that used to acid anhydrides. So
yeah, they're the ones that have the asymmetric and symmetric stretch, right? And first of all, on acid anhydrides, right? So first of all, we get a very unusual peak position where here it looks like we're somewhere around 1820 And at least on this particular one, this was just a simple aliphatic anhydride. I think it was isobutyric anhydride. And we're seeing something at about 1740 centimeters to the -1. So we're talking the asymmetric and symmetric carbonyl stretches. So what happens in acid anhydrides is you've got two very close to each other functional groups. And so you get coupled vibrations where either they go asymmetrically or they go symmetrically. So you get two bands. And we're way at high wavelength, way at high wave numbers, because basically you've got an electron withdrawing group here. And so that carbonyl, remember we talked about how that carbonyl is pushing down. We're actually where we have a stronger CO bond, right? Similarly, an acid chloride also is above 1800. So basically an electron withdrawing group will push us even beyond 1800. By the way, I misspoke in class and I felt very embarrassed where I said acid fluorides, the fluorine is more donating than withdrawing. I was absolutely wrong. Acid fluorides are even higher in wave numbers. So does that help you with that a little bit?
Thank you.
Yeah. Yeah, this is, and you know, one of the reasons why I really do this as a closed book part is the core knowledge is just so critical on reading spectra. And I'm going to come back to this when I talk about part 2 and some of the misconceptions people had. So I'll come back to that when I talk about the functional groups there, and particularly about esters, because I want to sort of integrate our knowledge. And I really believe that being able to have this at your fingertips is just integral to sort of reading. Other questions on the IR problem? So the mass spec problem was, there were sort of two concepts that we were working here. One was the concept that more carbons give you more C13 in the molecule. So by the time you're up at, you know, over 100 carbons or over 90 carbons, your biggest peak is your M+1 peak, or in the case of, you know, 180 carbons, it starts to become M+2. And honestly, for isotope patterns, if you've just got carbon, hydrogen, oxygen, and nitrogen, it's basically carbon that dominates it. C60 has a big M+1 peak, but it's not the biggest. The other concept I was working in here was that fluorine and phosphorus are monoisotopic, and I didn't put in a phosphorus compound. I probably should have, but I just put in PFOA, which I thought, you know, it's a common contaminant from nonstick cookware and other sorts of perfluoroalkyl compounds. One of these environmental things that doesn't break down, and we probably all got it in our body and so forth. So it's just a C8 compound, and that puts it over here. And then we had two compounds that had chlorine and bromine. Chlorine and bromine both have two isotopes that differ by 2 very characteristically. So chlorine has chlorine 35 and 37 in about a 3-to-1 ratio. Bromine has 79 and 81 in about a 1-to-1 ratio. And so by the time you have multiple chlorines in the molecule or multiple bromines, you've got substantial M+2, M+4, M+6 peaks. And again, we see both of these in the chlorine and the bromine compound, but with the bromo compound, we have, you know, we're further shifted because it's 1-to-1. So this is basically the pattern you get for 5 bromines here, and this is the pattern you'd get for 5 chlorines. So I was just playing off of that concept, and most people nailed this problem. I think a few people got confused, which was why I was going it over. The splitting trees, the only thing I really wanted to say, I guess maybe one person had trouble with a triplet of triplets. The only thing that broke my heart on this problem was the fact that on the ABX pattern, so this was basically everyone got the positions for resonance A and B. Everyone was able to understand the splitting patterns for the doublet of doublets. But the thing that's characteristic about an ABX pattern is that you have them tenting in when the two resonances are close to each other. They tent inwards. So I think our pattern was basically something akin to this. And there's a formula you can use to calculate the relative heights, but we didn't even go over it. And the main thing was only some sort of recognition that you would see some type of tenting in behavior in these ABX doublet of doublets here. So sort of broke my heart on this one. You know, in the end, I don't think it broke anybody's score, but I was looking for some type of evidence of them leaning into each other. And the X peak basically far away in chemical shift is purely a first order behavior. So the ABX behavior is the sort of simplest, or the AB behavior is the simplest of non-first order coupling patterns. It's the simplest. I guess if I was doing that, I'd make these two lines just a hair taller so that basically they're proportional. Anyway, AB pattern, and we see an AB pattern in problem number 3, which I want to come back to. We see a lovely AB pattern for a benzyl ester, which I think most people who attempted this one recognized in that problem. We'll come to that this was an AB pattern in problem 2.3 associated with a benzyl ester where we had a stereocenter off over here. Any questions about this problem? All right. I think, honestly, I didn't have any great comments to take away on the pyridine problem, the dimethyl pyridine problem. We had an absolutely wonderful Friday night session for people who came to hang out. And I guess I stayed from about 5 to 7, and then I think some people stayed till about 10 or 11, and I sort of checked in at one point. And one of the problems that I know people had worked on there was a very closely related methylpyridine problem. So some people really got the benefit of some of those old problems that I post. So as I was going through this and putting this problem together, James and I were talking, and he's like, well, can we really see this from the coupling constants? And honestly, my goal is more for people to learn than to get tested with exams. And I really wanted to give you the skills that you needed, because my goal is basically that the exam is just a learning experience. So I urged people to pay attention to all 3 things: coupling, symmetry, and chemical shift on here. Basically, you get, for the hydrogens that are next to the nitrogen in the pyridine, they end up being substantially downfield. So they're greater than 8 ppm in all of the compounds that have hydrogens next to there. And then you're able to deduce by symmetry and coupling. I don't have much else to say on this on this problem? Does anyone have a question or a comment on this? All right, let's move on. Let's move on. I don't, honestly, everyone did great on problem one. I think 14 out of 15 people did that problem. I think everyone was able to recognize from the mass spec there was a nitrogen in there. You got a nice carbon count from the C13 NMR spectrum. The one thing that's sort of cool, and I'll just point this out because I get a kick out of this, is there's a big difference, or at least to me, a noticeable difference. Oh yeah, I know something else I want to say about this as well. There's a noticeable difference between anilines and aliphatic amines, particularly like aliphatic secondary amines. The nitrogen is donating its electron density into the ring. You end up usually with a very well-defined NH stretch, and it's not that good a hydrogen bond donor, but more importantly, with that lone pair tied up by resonance, this nitrogen is not very basic at all. The pKa of an aniline is about 5 for the conjugate acid, whereas for a regular amine, the pKa is about 10 for the conjugate amine, 10 or 11. And so that nitrogen doesn't particularly like the hydrogen bond. So you can see very nicely a free NH. In fact, usually when I work with secondary amines, it's darn hard if the molecule has any size and it's a secondary aliphatic amine. It's often darn hard to make out that NH stretch. But here we see it clearly. We also see the nice NH bend. The other thing I guess I want to point out here, and this is more something, well, it's something useful. So the Aleph, actually, I'll go into the expansion here because it's a nice expansion. I think everyone has the hang of this. So in anilines and phenols, basically in compounds where you've got a good resonance donor on the ring, you really shift the ortho and paraproton upfield. It's sort of noticeable in phenols and very noticeable in anilines. That nitrogen is just super good at pushing electron density in. So your ortho position is very electron rich. And notice where we're showing up. We're at 6.5 ppm here. To me, in reading that spectrum, that just screams that there's something interesting. And you'll notice the para position also is pretty electron rich. It's maybe 6.6 ppm or thereabouts. For phenols, it's a little bit less noticeable. Phenols would be somewhere around here, but it's still noticeable. They're outside of that sort of normal 7 to 8 region for a plain vanilla aromatic. Just like I said in the pyridine, that region above 8 was sort of cool. The other place, so I guess I'll put phenols over here. And then as I was saying, at the other end, not in this compound, but when we have an acetophenone or any sort of carbonyl, that'll bring this proton here, the ortho proton, that'll bring it darn close to about 8 ppm or even a little bit greater, depending on the configuration. So there's a lot of good stuff to be read in the aromatic region here. Let's see if there was anything else on this one that I wanted to say. I guess the one comment, I hope by now, I'm pretty sure by now, everyone knows that even without a without a depth spectrum, you can just, your quats are so obvious in the C13. You're not getting a nuclear Overhauser effect, making the peaks bigger than they'd be, bigger than the Boltzmann distribution. The relaxation times tend to be long, so the peaks tend to be small because you're not having magnetization return. But I think everyone knows that by experience right now. Thoughts or questions on this problem? All right. This next one, this one was tough. So this is part 2.2. And I think maybe two people got the answer. I was really worried when James and I put this problem together. And in part, I was worried because I wasn't sure if it would be doable. The ones I saw a lot of answers that had esters in them, and that kind of concerned me. So I saw a lot of problems that had esters, and certainly a methyl ester makes sense because an aromatic methyl group is going to be about the same no matter what. But this led me to believe that maybe people weren't reading the spectra as well as they could. And so we're right at sort of a characteristic plain ketone position over here is sort of the first thing. And of course, NMR and IR talk to you together. And so, okay, if you didn't catch that right, we're at 1704. So that's sort of right in the sort of normal plain vanilla ketone region. In the C13 NMR, we're up at what, about 200 and I think 206, 200 and what are we at there? 208. And there's just no way that's an ester. And so that I thought was sort of cool. So in reading the spectra, I encourage people with functional groups, you're doing this not for my amusement, but actually to help focus yourself, so basically we come away with a ketone talking pretty strongly to this. I think just about everyone got the gist that when they looked at this molecule, almost everyone got that it was a 1,2,4 trisubstituted aromatics. But not everyone. There were a couple of 1,2,3 trisubstituted aromatics in there. And the coupling pattern just screams out for this. And this is, again, what I'm talking about with sort of reading our spectra. We've got one peak that's got metacoupling to it. Even if you don't calculate the J's, you can see it sort of screaming at you. One peak that's a straight up doublet. And one peak that's a doublet of doublets that's got your ortho coupling and the meta coupling going on. So that was something else I was hoping people would read from there as a takeaway. So I was hoping that basically people would sort of recognize 1,2,4 trisubstituted aromatic. There was a methyl at about 2 ppm, which could have been a CH3 on an AR, or could have been a CH3 next to a a carbonyl. I was hoping people would read that. I was hoping that people would read a CH2 chain in there. I think there was a pretty clear OH from the IR and the NMR. What I didn't know, or at least from the IR. So what I didn't know with this 1,2,4 trisubstitute aromatic is how people would put all these pieces together. And today I was sort of hinting how nice it would be to have HMBC, because HMBC would tell us exactly where our methoxy group was. It would connect the chain to the ring, and it would help put all of this together. It would connect the methyl group to the carbonyl. But I figured I'd see some interesting answers. So I was thinking about how many answers were possible. And if we assume that people had narrowed this down to being a catechol, a resorcinol, or a hydroquinone. I guess I'll actually, for the sake of parallelism, I'll just keep things sort of in the same place. Then there's still two possible connection points for this chain. There's a connection point over here. There's a connection point over here. And both of those would give 1,2,4 trisubstituted aromatic. And ditto here and here. And ditto here and here. So potentially there are six compounds. And I was thinking about this and thinking about how hard this problem really was, which was why I was very pleased for people who got close on the answers. But I had sort of dropped a colossal hint when I was talking in class about calculation of chemical shift. And I was really thinking about this in the carbon NMR. And it's interesting because ChemDraw just nails the chemical shifts within a ppm or a couple of ppm for carbon-13 shifts on a simple substitute aromatic. And so when I looked at that, the hydroquinone absolutely is out of the question, and the resorcinol are out of the questions. Now, among the two possibilities, in other words, among having the methoxy group where I've drawn it versus the alternative of a methoxy here versus a hydroxy, I'd be hard pressed to tell based on the carbon-13 NMR shifts. They are virtually the same deviations, small deviations. Carissa, you had some insights on this. Do you want to tell me your thinking? Because I saw you went with some proton shifts, and I thought it was really insightful.
Oh, thank you. I guess, let me.
In fact, I'll stop. Well, I can go to, I think you went to the proton NMR.
Yeah.
And you were looking, I guess, again in this region here, right? You were looking, I guess you were looking basically right over here, and you had some comments about the hydroxy group on this, right? Because you put the hydroxy here, the methoxy here, and the alkyl group over there. And I guess trying to remember, it was hard. I mean, on it, do you have an idea or thought?
Well, I'm trying to remember what I was thinking.
If you don't worry about it.
Well, I looked at the Like you're asking me why I put the R group where I put it?
Yeah, or to put it another way, another reason, because I thought it was really insightful. And I was looking, it's like, boy, I wouldn't have been able to tell these two apart. And I know, and the carbon shift calculation was pretty much dead on. Oh, Oh, was it that you were figuring that this was more upfield because the hydroxy is a better pusher? I'll be darned on this.
I'm pulling up my test to see if I made any notes on that.
I know it was right on one of the pages and I was impressed, but if you don't know, don't worry about it.
It might have just been a lucky guess. I don't know.
That could well be because I try to work these problems as blind as I can, and obviously I know what they are, but I try to basically forget and work through with a fresh mind, and which was sort of fun because it's like, well, how in hell do I tell the catechol from the resorcinol from the hydroquinone? And that the differences were very dramatic in the C13 shifts. Well, we will have, I'm not going to dwell on this anymore. We will have some new tools at our disposal in the next part. What I might do is, yeah, well, I'll take one moment here. I will flash up my ChemDraw. Let's see if I have this here. Yeah, so I ended up taking all 6 possibilities and said, all right, all I can do is tell the quats from the non-quats, from the methylenes, and just use ChemDraw, which is basically the same as what I showed in class with Silverstein. And darn, it was a good match for the resorcinol. And honestly, if you look at this, the other resorcinol was pretty much comparable, off by a ppm or 2. But the hydroquinones were terrible matches. We were, at 153 versus 146 for the highest one, or 150 and 149 versus 146 and 144. And the resorcinols were even worse because they're pumping electron density, or I guess pulling electron density, and so 158, 156, thereabouts. Anyway, I had fun with this. I'm not sure everyone else did in the same way, but very useful tool for basic chemical shift calculations. All right, let's take a look at problem 3. All right, so problem 3, I'd say of the people who attempted this, most probably did not quite nail it, but some did. Whether I draw it or not, you have a stereocenter right over here. The two benzyl protons are diastereotopic. The two methyl groups are diastereotopic. And I guess what I wanted to say on this, I think we got a variety of patterns here that people did. One of the things I saw, which I think I saw some that were kind of like this as a structure. And I guess the thing that would be cluing me in that maybe that's not the case is I'd expect to see J coupling then to all of these hydrogens here. And we see a doublet. But the other thing I guess I wanted to draw on was this recognition of this really interesting pattern that right, so here are diastereotopic methyls. I think most people recognize the idea that these were two separate methyl peaks. I think many people recognize they had a doublet over here, but I think some people didn't really maybe know quite what to make of this. And this is cool because at first you'd look at this and you'd say a quartet, but it's not a quartet. And we can see that the line spacing isn't equal. So it's a doublet, and they form an AB pattern. Right, we've got a stereocenter in the molecule, all the methylene groups in the molecule, all the isopropyl groups are diastereotopic. Generally, the further you are from the stereocenter, the more likely the protons are to end up dead on top of each other, in which case you'd see a singlet. But here in the benzyl group, they're not dead on top of each other. So we have this lovely AB pattern. I think it's about 12 hertz. So basically we have one of our doublets over here at about 5.19. I don't know, I haven't read it off of there. And another doublet over here at about 5.14 ppm. But it was such a lovely example of an AB pattern. And so that was probably the only thing I wanted to say on that. Any other comments or thoughts on this?
James, so I have a hard time putting these two peaks together on the molecule. So that's all, I think, the reason why I didn't get the structure. And then I couldn't figure out where the doublet that has one proton is.
Ah, this one. Yeah.
Because like I was thinking, okay, it cannot be like two protons, but it has to be a doublet. And then
so that proton, yeah. And sometimes I gotta say, I mean, sometimes things just don't come together, and that's not unusual when you're working a problem. Sometimes it's really hard to get all the pieces to come together, and you head down a blind alley. Yeah, I mean, in the end, we've got each of these methyls is a doublet. They're diastereotopic. We've got this methine, which is split quite heavily, probably technically a doublet of septets. The NH isn't coupling, the ammonium isn't coupling. And then we've got our diastereotopic CH2 group. But I would say if you didn't get this structure, you were in good company, because a lot of people didn't get this structure.
James.
Yeah.
I just really wanted to draw attention to the fact that the benzylic protons, those geminal protons to one another. They're in a completely different spin system than the stereocenter, and yet they are diastereotopic to one another. I just wanted to draw attention to that because when James and I saw that in the proton, when we were considering this for a problem, we thought that was really interesting. That's where the AB pattern arises from. No, sorry. Yeah, that's where the AB pattern arises from.
And it's interesting, this problem kind of harkens back to the epoxide problem that we had. I think if I remember correctly, was this the structure of the epoxide that we had? Or was it?
Yeah, I think so. That looks right.
Yeah. So it's sort of, this one was another beautiful problem because we have one stereocenter in the model. Everyone remember this one from the homework? Am I misremembering what the structure was?
I'm pretty sure that's the correct structure because you saw the exact same AB pattern where it appears to be a quartet, but the coupling constants are not, it's not a quartet.
So James ran this spectrum at, what was this? This was done at 400 megahertz. And had he run this spectrum at, let's say, on the 600 megahertz, what would have happened would be each doublet would still be at the same position, but now they'd be centered at the same position. But now what would have happened would be they would be slightly further apart in hertz, which means your tenting would be slightly less. And actually, if James had run this on 600, you might well have said it was a quartet because they might have looked a heck of a lot like it. They probably wouldn't have been perfectly 1 to 3 to 3 to 1. So if you ever had wanted to check and say, am I understanding this right? You could have, so this was 400. This would have been 600. And so you could have gone ahead and run it on the 600. And if this was really just a single pattern rather than two different doublets, then it would be exactly the same. So had there been some weird coupling and had there not been diastereotopicity, you'd see the exact same line spacing, but I can't think of any pattern that would have given rise to this that wasn't from two separate protons. Other thoughts or comments? All right, last one I wanted to talk about. I think most people who did problem number 4 got it. And it was a fun problem. So in a way, it played with many of the same concepts that problem 3 played with, and it brought into the concept of stereochemistry and symmetry. And so whether I draw this as a wedge or not, we have to remember that whether I draw it as a wedge or not, these two hydrogens are diastereotopic. And these two are diastereotopic. And these two are symmetrical. And these two are symmetrical. So we end up seeing these symmetrical patterns, and they all J-couple with this hydrogen. So we see that. And that was one of the things that appealed to me about this problem, was it also brought in concepts of stereochemistry. And we see, well, our good friend, the ABX pattern. It's a little more complicated because technically, this is actually an A prime, B prime, X spin system. But we see a very nice ABX pattern here. And this proton here, I suppose, is split into our good friend a triplet of triplets that we saw in the sketching problem, in the part 1 problem. And you can kind of see, we see 1, 2, and the third is buried right under here. And then we also pick up the other line for this. So this would be 2, 4, 2. And then since these two are adding together, we basically go 1, 2, 3, essentially 4, 3, 2, 1. It's not exactly that because the lines aren't exactly on top of each other, but basically we're something akin to that. And you could work out the J's if you want. But what I really wanted to do in this problem was to bring back this pattern here. And when we had talked about non-first order and pseudo first order patterns, I think I talked about dioctyl phthalate. Technically, it's a branched isomer. I talked about dioctyl phthalate. And I think I talked about orthodichlorobenzene. And I said, basically, no matter what you do with this, you're never going to see first order behavior, whether it's an A prime, X prime spin system, or if they're close to each other, A prime, B prime. These are pretty far apart. You are always going to see something very funky. And I admonished you, if you ever run your reactions with a Tygon-Schlenk line, you're going to get dioctyl phthalate oozing out of the Tygon into your solvent. And then when you strip your sample down and take an NMR spectrum, you're going to wonder what this pattern is. So this is our ortho-di substituted aromatic pattern. I don't know whether people, and most people who got this, I think, who attempted this got it right. And I don't know whether people did so recognizing that pattern or not. And anybody who got it right, I would love to know your thinking on this.
For me, I was just thinking that these two peaks could be like the proton shifts might be very close to each other. And then these peaks don't look like one peak. They look somewhat overlap onto the other ones. So I'm thinking this might be 2 proton peaks. And since there are 2 peaks and then each peaks are 2 protons, these 2 protons must be like kind of similar to each other. So that's why I have the symmetric.
Cool. Any other thoughts on this? Thank you. Thank you, Han. All right. Well, I've yammered on for a long time. I know James wanted to take at least a minute or two to share something. Do you have enough time to
Oh,
do
I
that?
absolutely do. I'm just going to blast right through. Let me connect my document camera. So everyone should be able to see and pin my document camera video.
Does everyone know how to do the pin on this, the pin video?
All right, so we're looking at problem 8.29a from the homework, and I sent an email last night clarifying we did move it to Wednesday, so it's due Wednesday. We're just going to discuss 8.29 and 8.34 because they're the most difficult, and there's some ambiguity in 8.34 that James and I would like to clear up with everyone so that you're not beating your head against it for too long. So there is a formulaic approach to NMR structure solving problems that James will literally give you a handout that has that very formulaic approach later in the course once we've discussed the usefulness of every type of 2D spectra that you can take. And so when in doubt, you can follow that in order to give yourself as much information as possible about whatever problem it is you're doing. If along the way you make an inference that allows you to put a piece together that you don't technically have other information for yet, do whatever makes sense to you, as long as it makes sense to you and you arrive at the correct conclusion. But I usually take this formulaic approach because it's nice to me to have all of the information in one place. So if we're looking at 8.29, goal number one for me is always going to be to find the molecular formula. I look to the IR for functional groups, obvious alcohol. So I'm already thinking I probably have an oxygen in here. I tally up the protons. I got to H16. Remember that if there's symmetry, this doesn't necessarily mean you have exactly 16 protons. It could be 32 and it could be symmetric. It could be a different number because you have symmetry. So keep that in mind when you calculate your molecular formula. I counted 8 carbons. That just happened to match our molecular weight, and it gave us 1 degree of unsaturation. So I'm looking for a degree of unsaturation. I don't see it in a ketone, so I'm thinking alkene. I tally up all of the protons, and where possible, I try to identify what the coupling pattern is, and occasionally also Hertz coupling values, because especially in this problem, that becomes useful later on. So I tally up all of the information that I get from every spectra. So like I said, mass spec, we got the molecular formula. IR, I got a functional group. Proton, a lot of these look like multiplets, but I see a couple of protons that integrate to 3. So there are methyl groups. One of them is a doublet. So that is a fragment in and of itself. Then I move to the carbon. In addition to making notes about chemical shift along the way. So we have 2 carbons, a quaternary carbon around 130, another carbon around 125. We'll keep that in our back pocket for later. I use the depth to tally up what type of carbon every one of these is. And so now we know which carbons correspond to our, let's see if it'll focus, which carbons correspond to our methynes and methyl groups, which puts us in a good position for, in this case, it was a het core, but we discussed how this is similar to a cozy experiment in class today. This spectrum was much kinder than 8.34 is. You're able to pick out most of your correlations relatively easily. So once you know that, for example, proton A is on carbon 2, you have all of these proton-carbon correlations. And I, just for my own thinking, I write those out so that I can start forming a picture in my head. Okay, if 4 is a methylene, and it looks like I wrote G and G prime because I'm anticipating that these are diastereotopic, those in the spectra, it doesn't look like a clean pattern. It looks like 2 protons that are overlapping with one another, so I call them G and G prime. So I'm anticipating, okay, if I have a methylene and they're diastereotopic, I probably have a methylene chain at some point, and I'm looking for this to bridge together connectivity between 2 different fragments or something similar. Then you move into the cozy. And once you tally up your cozy correlations, for this problem, it actually very nicely makes a bridge from, and let's see if I can get 2 things on the screen at the same time, from 2 to 6, from 6 to 4, from 4 to 3, and from 3 to 7. So just like that, once you have your cozy correlations, you can make a 5-carbon chain, and then I'm already running low on time, so I suppose I'll leave this last part to you. We're missing a couple of carbons, and remember that proton-proton correlation doesn't necessarily have to be 3 bonds, and we were missing a degree of unsaturation, so that should give you a hint as to what we're expecting later on in the structure. But this is the power of HMQC plus cozy in allowing you to put together a 5-carbon chain from otherwise disparate carbons. So now let's move to 8.34. I did the exact same thing, and spoiler alert, these structures are similar to one another. So alcohol, counted the protons, counted the carbons, no symmetry. This happened to match the molecular formula exactly once you accounted for the alcohol and the IR. I I didn't have a good time with the cozy correlations.
Yeah.
HMQC, you can get closer, but the problem with this problem is there is so much overlap of these individual single protons. So, okay, A is a methine, that's fine. B and B prime, we're getting into maybe a diastereotopic methylene because this is still well separated from everything else. But then we have 3 chemically inequivalent protons all under one sort of huddle. I called this F and F prime, I called this G and G prime. And conceptually, we understand what diastereotopicity means for 2 protons that are chemically similar but still chemically inequivalent. However, in correlation experiments, unless you're able to zoom in really well, or unless you can infer something about the shape of the little correlation blot, you have this trouble of, well, I'm not sure if that's coming from the G proton that I have assigned to be on carbon. Well, let me rephrase what I'm saying. Because of this ambiguity between whether, all right, sorry, one more time, I'll get it this time. In my HMQC analysis, I found that one of the 2 F protons is on, at least one of the 2 F protons is on 4. Carbon 4 also has a G proton on it. Carbon 5 has one of those 2 inequivalent G protons on it. And 5 also has an H proton on it. Therefore, when you try and draw correlations between protons F, G, and H in the cozy, if you're being complete and you're not making assumptions, any one of those correlations could be the significant one that you have to derive from this. So I made an assumption when I was bridging my correlations together. I started from carbon 2, which had correlations with these 2 methyls. And I put a question mark next to this because, again, this connectivity is not necessarily correct. Remember that you can have 4-bond coupling, and I'll leave everyone to that. I made a bridge between carbon 2 to 8, and then it could have been either 4 or 5. I knew that carbon 6 was correlated to both 4 and 5, so I just sort of put it in between these 2 carbons. One of our methyl groups is correlated to proton F, which is on carbon 6. And then you can continue your skeleton out to carbon 3, which happens to be adjacent to the alcohol. But this region right here, if you did not know what the structure you're going for is ahead of time, you'd be hard pressed to deduce that given the amount of overlap in this spectrum. So I just wanted to, well, James and I both wanted to go over this part in discussion to point out that this methyl group happens to be 1, 2, 3, 4 bonds away from the alcohol. And again, I'll let everyone figure out what this terminal functional group is on your own. Note that I haven't assigned the quaternary carbon in this skeleton. Are there any questions about any step of that sort of problem-solving process? If anyone has follow-up questions about 8.34 that you have before Wednesday as you're working on this homework and trying to tabulate all of those correlations yourself, please feel free to email me. I'd be happy to discuss this problem in more detail. The very last thing that I want to show everyone before we're really, really out of time. Oops, hello everyone. So this is, everyone can see my top spin screen. Okay, this is the HMQC of strychnine that I recorded last night, 2 nights ago. What does time even mean anymore? So if I scroll my mouse wheel in, we start to get into noise. If I scroll my mouse wheel out, we no longer see any correlations. Defined levels are outside of data set range. What does this mean? What does it mean when the blobs are getting bigger and smaller? Well, Topspin has a contour plot visualization feature. It also has oblique mode. So check this out. This is a topographical representation of these correlations. So it is possible to rotate this view. It's not particularly easy to do. But remember, we still have our F1 domain along here, our F2 domain along here, and that is, so our F1 is our carbon, our F2 is our proton. So we still have our carbon spectra that we can plot in our minds here and our proton spectra here. I rotate this just so, yeah, there we go. So that is effectively what topspin is showing you. But if you wanted to, you could dig into the topographical representation also. And if you zoom in, you'll see sometimes very weak correlations are shallow. And so they don't necessarily show up if you zoom out, but you can zoom in order to make those show up better. And then if you zoom in too much, you get into noise. Does that make sense, this topographical representation, how it correlates to the contour map? Okay, sweet. I got through, I just heard James's grandfather clock, so I think I'm out of time.
So I will chime in one last comment here. I would say on 8.34, probably placing the methyl is well nigh impossible, but this sets the stage for other techniques. Later on in the course, I'll introduce HMQC toxy, and the frustrations that we are going to experience up until I introduce it, the frustrations through overlap and the inability to walk your way through with the cozy will make it all more clear how this tool can be useful in your toolbox. The other thing I'd like to add here is I think it's absolutely fantastic the way James is dealing with ambiguity, where he's using that 4/5 notation. This is great because you'll get stuck and you're like, well, how do I deal with this if I don't know? And then you can't go further. And saying, well, okay, right now I don't know. It's either 4 or 5. We're going to come up with one case where it's another molecule, very beautiful molecule with some isolated methyls on quats, and we'll be using HMBC. And we can't tell whether the quats are 2 or 6. And we'll just go ahead and say 2/6 for each of them. And then you can move ahead and say, okay, I don't know. And at the end of the problem, you still probably won't know which is 2 and which is 6, but you're going to have been able to put all the pieces together. So great problem solving strategy overall that James has done here, sort of laying everything out and helping keep yourself organized as you work through these problems. So guarantee you will become really good at this as you start to work through.
It's really fun too.
Yeah, and I urge people to set up study groups and study sessions. I think people were having a good time on Friday night. Maybe I'm reading it wrong, but I think people were enjoying themselves working together. So
yeah, I was having fun for sure. I will second that, James.
All right. Well, thank you for going ahead and confirming that. I'm going to, unless there are any other comments, I think I'm going to let everyone go.